All right, so continue. So the next, let's look at this example. So find the geometric description. Okay. So in space, okay. So the first one is x equals 3, y equals 5. Okay, so what does that mean? So keep in mind we're talking about space, and you know. So this is 3, this is 5, right? So x equals 3, actually it is a line, excuse me, it's a plane, right? That is perpendicular to this x-axis and crosses 3 here. And y equals 5, it's the same logic. So you're going to have, you know, another plane, right? So you will see that actually when x equals 3 and y equals 5, actually those two planes, they gonna intersect. So the intersection for both of them is gonna be a line, right? So it's a, so you can see that it's a line that two planes intersect. Okay. Or right, so or you can see that it is a line that it is perpendicular to the xy plane and through 3, 5, 0, right? It's more specific, right? So as you can see. All right, so that's the first one. Second one is x squared plus y squared equals 9, and z equals 81. Okay. So again, excuse me. So if we draw this, and you will see that if in space, when x squared plus y squared equals 9, it's not a circle anymore. Actually, it's going to be a right, it's going to be a cylinder, right? So you can see that. And we'll add one more condition here. Z equals 81. Z equals 81 means what? It is a plane, right? That is perpendicular to the z-axis and intersect with the 81. So basically, what it will show here is so this other circle, right? With the condition, you know, x squared plus y squared equals 9, and z equals 81 here. So that's kind of like the geometric description, as you can see that. Okay, so well, you can see that it's a circle, and with this property and the z coordinates equals 81. So I think the best way to explain this, maybe it's like to show this visually. So I think that probably is the best way to understand. Okay, so that's one simple question. And continue. All right, so next one is you know, give you a point P 0, 0, 1, Q 2, 0, 0. R 0, 3, 0. So find the vector projection PQ on to QR. Okay, so basically, right. Okay, so that's the problem. And to talking about this part, guys, this is what I would like to. So suppose this is like the vector. I don't know. So suppose this is a vector PQ. Okay, suppose this is vector QR here. Okay, so and you see that I'm looking for the projection. First of all, it's in itself it's also a vector, right? So also it's a vector. So so you can see that this projection vector, it has two components. First, we need to know its magnitude, which is the magnitude of PQ times cosine theta, right? So that's the magnitude, right? And then you will also need to time the direction unit vector. So that is actually it's a QR, over its magnitude. Okay, so that's like the big picture of the meaning of the projection of one vector onto the other vector. Okay, onto the other vector. And so you see, normally I don't remember like the formula of this, but what I like to remember is I remember this graph. And also on top of that, the other thing I would like to remember is I need to know that what's the meaning, what's the geometric interpretation of the dot product, which as you can see that if we do a PQ dot QR, so that dot product means that it's the right? So that's basically the definition of this dot product here. So with this in mind, you will see that we can get this magnitude of pieces is going to give us is a PQ dot QR, and then so it's over the magnitude of the QR. So put it all together here, guys. So this projection of so it's a PQ onto QR is going to be PQ dot QR over this Q magnitude of QR, right? And then times, so that's the magnitude, which is this part, and then times QR magnitude of QR. Okay. So keep in mind, this is a scalar. This is also a scalar. So only this part is a vector. Okay. Okay, so we can even simplify a little bit more into PQ dot QR over the QR magnitude square, and then times the vector QR. Okay. And also another property about the dot product is QR dot QR. You're gonna have its QR magnitude square. Okay, so that's another thing. So this formula actually can be treated as QR dot QR, and then times the vector QR. Okay. So right now, you see this is going to be the finalized formula we would use to figure out this problem. So as you can see, the PQ we have it here. So it's a PQ, vector PQ is going to give us, it's a 2, 0, negative 1, okay? vector QR is going to give us its negative 2, 3, and 0. Okay, so with those two, we can do whatever we want, right? So as you can see, PQ dot QR, so that gonna so let me write it here. So excuse me, so it's PQ vector, it's 2, 0, negative 1. QR, it's negative 2, 3, 0. So the dot of those is gonna be negative 4, right? So negative 4 plus 0, and then plus 0. The QR dot itself, so it's negative 2 times negative 2 is 4, and then plus 9, and then plus 0, right? And then times this QR is negative 2, 3, 0. So it turns out this is going to be negative 4 over 13, right? So it's if you multiply this part, so it's a negative 4 over 13, 0, so that's going to be 8 over 13, negative 12 over 13, 0. So yeah, so that's the projection for of PQ onto QR.